So, welcome back to the next tutorial in the area of cloud databases. It will be given by Norbert Ritter and Felix Gessert. Norbert is a professor of database in Hamburg. And before Norbert is allowed to start, after the session that Norbert and Felix is given, we have a session half hour by Flexion. We will stop at 12:30, and then we have a group lecture. So please, after 12:30, don't run away for lunch, but just we are meeting outside at this column of a place to have the traditional group picture. Right? So, Norbert, please.
Okay. So thanks, Frank. I hope everybody can hear me, so I have chosen the mobile microphone because I'm more than one running around during presentations. I understand something. As Frank said already, we are talking about scalable cloud databases. And actually, it's going to be a tutorial, but it's not really a pure tutorial because we have two parts. In the first part, I'll be giving a kind of overview of the basic notions of cloud, what is cloud data computing. Then in the second part, we will have a more specific project description given by Felix. And he will be talking about our approach because our approach is the only really acceptable cloud data management approach in the world to the best of our knowledge. So we can talk about this later on. So that means our presentation has the following outline. I'm going to give you motivation, and then we will have Felix will take over and he will give an overview of our Orestes project, and this is meant to be a really deep dive into the basic concepts of the Orestes approach. It has basically two parts. One is mechanisms for solving latency in order to be really scalable, and the other thing is to have all these NoSQL systems we have been talking about in the first talk this morning available at the back end, and kind of encapsulating all these specific features for the application in order to not burden the application with all these specific details, but having all the advantages of these systems available for the cloud data users, data management users. Okay? Which classes of cloud databases are there? This is pretty close to what Stu this morning have been talking about. We actually are talking about databases as a service. Yeah? What you can have as different categories, you can have cloud deployment of database management systems. So that means you have a database system and you deploy it on a remote infrastructure, somewhere else in the cloud, and then you don't have to manage it yourself. It's running out there in the cloud, but it's your responsibility to do the management of the system. You have cloud-only database as a service systems at the other end of this range. That means they are only available in cloud environments. Yeah? It's not a system that you could deploy on your environment. It's only available as a cloud system. And and in the same way, you can use analytics as a service. The other thing I want to go into a little bit is the managed variant of all this. So you can use different classes of database systems, for example, relational databases, which are managed by a cloud provider. So you can use them, but you are not responsible for managing them. In this case, you are responsible for doing the management and maintenance of all these things. And here you have these additional features provided by the cloud provider. The same way you can have these NoSQL systems as managed databases in the cloud environment. And so what we, additionally to these possibilities we have already in the literature, propose is to provide what we call backend as a service. And backend as a service is a little bit more than, for example, what we have in the case of managed database systems. At our approach, Orestes is one representative of these kinds of backend as a service systems, and we have, you all know that, this typical classical data architecture. You have, these operational online transaction processing systems, these operative database systems, and usually you additionally need some kind of analytics, and for that purpose we have traditionally used data warehouses and to do data mining and reporting. And this is supposed to be replaced by database as a service approaches. Yeah. So, and the message here is that the era of one-size-fits-all database systems is really over. We have all these specialized cloud databases. So, and Holger wasn't mentioning it. He gave us an example of all these different classes of NoSQL systems, but he also mentioned that these different examples do not really represent all the members of the respective classes, because they are really, really different. They all have specific features, specific advantages, and they were actually all designed for a very special purpose. So we have a huge amount of systems out there, all having really specific benefits and advantages. And that makes it really difficult for applications to choose the right system for the given purpose, to map the requirements of the application to the actual system. And this is why we will propose something like a polyglot persistence mediator, but we will go into that later on. So this is the first message. These are just examples for all these systems, database systems, and we have listed there some of the specific purposes they are really good and they are really designed for and they are really famous for. We have there relational systems, we have there the keyboard that we have heard about in the previous talk and so forth. And the same thing is true for those database systems which are available in cloud environments. They have really very specific purposes and benefits, and this is really why all these systems have been developed for very special needs. So this is the basic observation, and then we come to the actual topic of this talk, which is cloud data management. And we see cloud data management as being a kind of new field, tackling the design, implementation, evaluation, and application implications of database systems in cloud environments. That means we want to consider the whole path from the application via something we may call middleware or cloud provider interface or something, up to the back end where we have possibly several of these new database systems we learned about this morning. So, and if you really want to tackle this problem in a really comprehensive way, you have to care for many different aspects. For example, starting at the application side, you have to deal with application architecture, support data models. Then you have to provide protocols, APIs. You possibly have to provide caching for scalability purposes and so forth. At this middleware thing, you have to care for load distribution. We're talking about service level agreements and how to provide, observe them. You have to do workload management. You have to care for multi-tenancy. How do you map multiple tenants to your data backend? We were talking about consistency and availability and these things which were captured by the CAF theory processing, security, and then at the back end you have all these things the different systems provide in order to be really to contribute to scalability like replication, sharding, and you certainly want most of the traditional guarantees database systems do provide like transactions and all these things. Although many NoSQL systems do relax these properties, it's a kind of a trade-off in order to be scalable and highly performant in the era of big data, but the best solution would be to be scalable and to have asset properties, right? So, and this is what shows the whole range of the problem we have to tackle when we So we have some more tutorial-like classifications and overview pictures here. Cloud database models, you can look at these two dimensions, the data model and the deployment model. We were talking about the deployment model. You remember that we had cloud deployed systems, we have managed systems, and we have very proprietary systems. Yeah. This is the deployment model from unmanaged to managed, and these are the different structuring levels or degrees from structured to unstructured. And this is the whole range of systems we have out there in the cloud environment, and this is what we actually consider are being database as a service systems. We have the managed NoSQL systems, the managed relational data warehouse systems, and so forth. We have them managed in a proprietary way, as already mentioned. The cloud deployed database systems, as I told you, we have database image provisioned in the infrastructure of like a service cloud. What you can do is you can take one of all the systems we have talked about this morning. We have these four classes, document, white column, key value, graph systems, and deploy it in a possibly infrastructure as a service cloud. Yeah? Then you do the management, you just use the infrastructure which is covered by the cloud provider. That does not solve in order to motivate what we mean by managed and to show that having management features is a desired thing. That does not solve provisioning, backup, security, scaling, elasticity, performance, tuning, failure, repetition, all these things. That means if you just deploy your system like this, you have to care for this. Yeah. So, and this is not really desirable. So in the managed variant, you have the cloud-hosted databases, and there the cloud provider or the database as a service provider provides features for all this. Yeah? So he doesn't only offer the functionality of the data system, management system, he also cares for provisioning, backup, security, scaling, and so forth. And examples here are the systems. You have you manage relational systems. You have these NoSQL systems, and you also have data warehouse arrays. And I don't want to go in all these examples. I can tell you that Felix knows every detail about every of these systems, but if you have questions, please ask him afterwards. Okay, so then we have the proprietary cloud database thing. They are designed for and applied in vendor-specific cloud environments. They are proprietary, and they have to use the provider's API, and that's it. And examples are those for databases and those for simple object stores, providing very simple front APIs. The same is true for analytics as a service. Examples, just leave it like this, you're going to restrict Felix time afterward. So, and then we come to the backend as a service. So this is what we really want to propose and want to design and want to contribute to, because we think that this is the approach which really makes cloud data management environment being feasible systems. Yeah. So that means we have database as a service environment with embedded custom and predefined application logic. So what you have there, we have the data backend, we have a service layer, you have a backend IPP and a data API. And that means you have all these features you need additionally to the pure database systems functionality, like authentication, user management, validation, and so forth. We go into that later on. And you have kind of automatic mapping to different database systems. So what we really want to have is that we can use many different of these NoSQL systems at the back end, and some kind of support for the users and the application in terms of mapping special structures, special needs to the right system. Yeah? By not having the application to know all the details of all the systems. Yeah? it's a kind of, we can discuss about how automatic this can be, but we actually would aim at a kind of automatic mediation between application needs and the polyglot backend. So there are already out there some backend as a service systems, but on one hand we have these managed cloud databases. That means they emphasize the data backend. They provide database features through the system they deploy in the cloud, and these available backend as a service systems, they have only very, very, very basic data management features. They provide simple structures and really only very, very poor CRUD functionality. Yeah. So what we want to do is we want to really combine the full range of features provided by the NoSQL systems and all these classic database systems, and additionally we want to support the overall path from the application over the middleware through the backend. And having all these in mind, I think we can say that the backend is this is the implementation of Orestes. Orestes approach is the one which really the most comprehensive, mostly encompassing this spectrum of features. Okay, this is not very exciting. You can have for database as a service environment different pricing models. They can be pay-per-use or plan-based. I want just to go briefly through that. You can have different approaches for managing multi-tenancy. Many tenants all using the system, you have to do some isolation between them. Yeah. So, and if you consider the usual stack of a system from hardware resources via virtual machines, database processes, database and schema and so forth, you can have different variants in terms of multi-tenancy management, which are different in the part of the stack which is specific and the other part which is shared of all tenants. Yeah. So if you have a private operating system, just the hardware resources are kind of shared and everything on top is specific to one tenant. Yeah. And then you have different variations of all that, and you can see different systems as examples of all that. Yeah. So in the most the right-hand side you see in the graph where everything up to the database schema is shared, yeah, and this is where most software service applications do. Yeah. So there are different ways to do that, and yeah, if you are if you try to assess that in terms of resource utilization and isolation, you can say that from private to shared, the isolation gets lower and the resource utilization gets higher. So this is again some kind of trade-off, and all these different mechanisms are out there. I just mentioned them because this is also meant to be tutorial, so just to give an overview on that. So the same is authentication, authorization is also needed in these environments on top of the actual data management. What you always have is you authenticate and do a login, then you have different possibilities to do this authentication. There are internal schemes, you can use an external identity provider, you can have some single sign-on, you get back a token, you use the token, you can send requests, and these can be checked again in different ways. I guess you already know from rule-based, role-based, by using policies and so forth. So this is what we require for this purpose, and you can do the response. Okay, I did this very fast because I wanted to say a few words about service level agreements, because I think they are very, very important in these environments. Most of you know, or at least briefly, what service level agreements are. You have a technical part usually consisting of different service level objectives. The legal part, additionally interesting for our point of view, are the the technical service level objectives like availability, durability, consistency, scale, and security response times. Yeah? So you, as a user of the cloud database system, can do kind of contract with a service provider, and he is supposed to guarantee these service level objectives. Yeah? This is what you get for the money you pay for the service. Again, we can still distinguish functional service level objectives. It guarantees usually they have transactions or they do not have transactions. Yeah? So this is a functional thing. More difficult to handle are the non-functional service level objectives, because here you usually have continuous things like response times, latency, and so forth. So how to handle that? We try to make service level objectives measurable through utilities. That means utility expresses the value of a continuous non-functional requirement. That means you have a utility function applied to some kind of metric like these, mapping to a value between 1 and 0. So possibly you can say latency gets a 1 for under 20 milliseconds of response time, and then you have this behavior. Yeah. So and then this function gives you a value, and then you can do workload management. That means you have workload classification classes, and then you try to maximize the utility. And possibly this is a very complex problem because you have multi-objective optimization problem. Yeah, what the result. And the interesting thing is, from the viewpoint of a service provider, that if you have an expected increasing load, he from time to time has to do some kind of scale out or something, yeah, to provide additional resources in order to be able to provide the power that is needed. But things are in reality not that easy, so what you usually have is something like that. That means you have times of over-provisioning, yeah, more resources than needed, or under-provisioning, actually more requests than power per the system. So, and that means this shows the complexity of the problem. Yeah? So if you have several of these objectives, and as a service provider you have to kind of minimize penalty, yeah, for not observing guarantees, service levels, and resource costs. Yeah? And this is a very complex problem, and everybody is talking about service level improvement, but nobody does have that. So what does system currently have? If they have something, then they are just talking about half-time. And this is actually pretty very poor. So this leads us directly to the open research question, how to do that in a reasonable way. We're going to be talking about consistency, which consistency guarantees can be provided in a geo-replicated system without sacrificing availability. So we want it all. We want to have a scalable cloud data management environment, and we want to have rich consistency. And we want to have high performance and low latency and asset transactions, if possible, and how we can, at least to some extent, go this way will now be described by Felix to kind of pass over.
Yeah, thank you very much. At this point, I'll quickly mention that. So, on the topic of cloud data management, we'll also be doing a workshop in Silicon Valley this fall. So, if you would like to submit a paper, the submission deadline is still open, and I guess it will be very interesting. It's a third conference workshop we're doing on this topic, and it's been enthusiastic with us. Okay, so I now want to dive into these topics from our perspective of the system we are building. And I want to cover two parts. The one part is if the application is geographically distributed, it's possibly okay, it's not. Okay, better?
Yeah, much better.
So, yeah, two parts. The first part is if the application is geographically distributed and possibly also distributed from the database system, how can we still guarantee fast, high-performing database access? That's the one question we're tackling. And the second one is if we have all those different systems that excel at certain workloads, at certain service level agreements, how can we combine those heterogeneous systems into a single view for the application? And our goal is, in our database as a service middleware, REST is to solve both problems. And I want to talk about how we achieve that. So first off, let me motivate why we need to do something about latency and performance. So an average website, as of this year, takes about 9.3 seconds to load and needs about 100 requests in order to get fulfilled, loading roughly 1.5 megabytes. And that's a really difficult problem because there are many studies that found out that latency is a very important factor for user satisfaction and business impact. So Amazon, for instance, found that if you lose 100 milliseconds load time, that already means that you lose 1% of your revenue. And if you have the size of Amazon, that's an amount of roughly $800 million per year. So definitely a problem even at that small scale. Similar studies from Yahoo, for instance. So if you use 400 milliseconds of load time, they did this through A/B testing. 9% of your visitors will drop out because they are unsatisfied with how the website performs. Study from Google, they tested, do users prefer more search results or do they prefer faster search results? And the result was quite obvious. If we take 500 more milliseconds to display more results, that's actually not well received by users because we take more time to render the search result page and the traffic goes down because users do not want to wait for the search result. And all these studies show us, okay, there's much of a motivation to solve this latency problem. So what can we, as the database side of all this application architecture, what can we do about it? So if we have these load times, what is actually the underlying problem? So from the database perspective. And from our point of view, there are two things. The first part is what we see here is a user in the USA accessing a database system or an application based in Europe. And when he tries to access that application, for instance, the website, we have two major bottlenecks in the processing. The one is that we need to assemble the web page on the server side. We have some kind of application server, we have a database, and we have to generate a view for our user. That's the first bottleneck. So that can be solved through various NoSQL systems. And the second part is, and that's much harder to solve, the high latency of delivering the actual content to the users because there's an in-between network and we cannot beat the speed of light. So we have some network propagation time which we cannot get around. And this high latency is actually what causes slow page load times. I've illustrated that here. So this is the throughput, the bandwidth of the internet connection compared to the page load time. So if we increase our throughput, we quickly saturate the page load time. So there's no gain from going from 5 megabits mobile networks to 50 megabytes broadband internet access because in terms of page load times, you do not get any additional increase in page load time. But if we can minimize the actual round-trip latency between the application and the web browser, for instance, we get a linear decrease in page load time. And that's what we're aiming for. We need an approach to minimize latency. So our vision is to serve data ubiquitously through an infrastructure. We do not need to build ahead of time, but we want to leverage an existing infrastructure. And there is an infrastructure for that called the web caching infrastructure. And the next part will show you how we can leverage this existing infrastructure by accessing it through certain protocols and by building an API and a system that is accessible through the standard HTTP caching protocols. And thus, if we have a user now accessing our European backend, we can now serve the content from a nearby web cache, possibly even from the browser cache of the user. And that solves the latency problem, and the other problem, the less processing, also leads to less overhead in the backend, so we also, on the processing side, gain something. And that's what I want to dive deeper in the next section, but first I'll let me motivate what the actual problem is when we try to leverage this infrastructure. So why is no one doing it? So the way classic web caching works is that every object delivered over HTTP, for instance over REST API, has a predefined TTL, a time to live, which indicates for how long the object may be cached. And for that time, every in-between web cache will store the copy of the object. So a problem arises when a different user or a different application tries to modify some data. In that case, we still have our non-expired objects in the web caches, and this data might be delivered to applications and they will see stale, inconsistent data. So we need some mechanism to tackle this staleness problem, and that's what it's all about. So how can we construct database services that leverage the web caching infrastructure for low latency, but also guarantee rich consistency? Okay, that's the first part. The second part is centered around how we then store the data at the database as a service side. And there we made the observation that the more complex applications get, the more different data systems they will employ. For instance, if we build modern applications, we might decide to structure or nested document structured data in something like MongoDB, or billing data, which needs transactions, might be stored in the classical relational systems. We might employ a graph database for storing something like a friend network, some in-memory caches like Redis or Memcache for storing metrics and caching, Elasticsearch or Solar for full-text indexing, Cassandra maybe for highly available session data storage, and file systems for blobs and recommendation systems, and machine learning systems for providing high-level analytics. So this is a very complicated architecture, but this is what is done in practice, because no single system fits all needs, and so we stick these systems together at the application level. And we think that's a bad thing, and therefore we want to automate this process of mapping data to databases according to the actual needs we want to fulfill with these systems. And we will express them through SLAs. So our vision is this. Suppose we have a database schema consisting of our fields, our tables, and so on and so forth. And now the application designer can decide which guarantees he actually wants fulfilled. For instance, he does want high write throughput, more than 10,000 requests per second, high availability for reads, scan queries, full text search, and maybe some consistency guarantees like monotonic read consistency. And we just want to declaratively define those in order to let the system decide how those can be fulfilled. And what we want to do with that is that we want to feed that into a system called the polyglot persistence mediator, which takes the annotated schema, which knows the available systems and their metrics, and now can make the decision, this incoming query, this incoming data, we can route it to this database because that's best for how this SLA is demanding, for instance, read throughput. Okay, and we'll talk about that. So, say we have defined latency smaller than 30 milliseconds, the polyglot persistence mediator can now actively schedule and route our request to the according database systems. That's the vision we have. So, first off, before I dive into how it's actually done, the overall infrastructure, the overall architecture is this. So, the system we're developing, Orestes, has these components in the backend where it does the polyglot storage, balancing over the database systems. It has this layer of providing the database as a service functionality, like the multi-tenancy, security, and most importantly, the caching part. And then in between the clients, so the applications and the server, we only use standard HTTP caching, no special infrastructure, and a simple REST API to make it accessible from any device. That's the overall infrastructure. Okay, so now let's dive into how we do this caching approach. So, as I told you, there are these existing web caches, and there are actually two kinds of web caches. The one are the expiration-based ones. That's the classic one. The expiration-based caches only get this TTL, saying this object is valid for 3 hours, and then they cache it for that amount of time. And there's no getting by this limitation, so there's no premature invalidation of the cache we can perform. On the other hand, we have the invalidation-based caches, which also do TTL-based caching, but on top of that, provide some kind of API in order to mark objects as expired, so they provide an invalidation interface. which is far more flexible, but of course, in a global infrastructure like your browser caches or your ISP caches, you cannot reach through and invalidate those caches, and therefore the expiration-based model is by design because it's far more scalable and doesn't need any coordination by the server. But in our approach, we want to stick together those two kinds of caches, the expiration-based caches and the invalidation-based caches. So what you probably know as an example of invalidation-based caches are contact delivery networks. They provide caching as a service, and they offer these invalidation capabilities. So what do we actually have to do in order to make this caching feasible for a CRUD database API? So what we have, what we need is that the client can determine himself, is there a need for revalidating the object? Is this object which I might get from a cache, is it potentially stale, or can I safely read it from the cache? And this kind of information, we need to encode it and need to get it to the client. And that's what we have to do at the client side. And at the server side, we want some kind of algorithm which tells us when do we actually need an invalidation and how do we construct this structure for the client. And this is what our cached cache approach does. It's actually a very simple Bloom filter containing all the objects that have been written before they expired in some cache, so all potentially stale objects. This Bloom filter, consisting of the objects, is due to its probabilistic structure as an algorithm feature of the Bloom filter is very small, so we can afford to regularly transfer the Bloom filter and also load it at startup time, for instance, of a web page, because it can be easily piggybacked because it's very, very small. It buys that small size. It's a set-based algorithm, a set-based data structure. It buys that smallness by allowing a false positive rate, and this false positive rate conforms well to how this caching works, because when we get a false positive in our Bloom filter, this only means we might revalidate an object even though it's still cached. So we do not lose anything, but we get just an unnecessary non-cache result. So that's not a bad thing, and therefore we can employ Bloom filters. And at the server side, we have the similar structure in order to track which objects are actually not expired and which have been written, and we construct this Bloom filter for the clients in a high-performant way. So if we have this Bloom filter at server side, we can transfer it with that connect tab in order to tell the client, okay, the page you're going to load contains several objects which do not have to be, which may not be read from caches because they are old, and then the client can do its regular page load. That's the startup way of transferring the Bloom filter. Then we can periodically transfer it. For instance, every delta seconds, we might do a transparent request of this cache sketch. For instance, on a regular load command, we might just append the Bloom filter in order to have it for the next request. And that way, we get a higher level of consistency, because no object we'll ever read from a cache will be older than this delta seconds. And we can also use it for transaction processing by loading it at the beginning of the transaction. So we have two tasks to perform. We have to minimize invalidations because those are costly. We do only want to invalidate objects which are actually stale, and we want to minimize staleness by having the client know when objects need revalidation and when they can be safely read from caches. So this shows the end-to-end path of a request using this scheme. So consider a web application we built, and this now does some kind of request in its JavaScript API. This gets mapped to some REST HTTP request, and this request will be propagated through this chain of web caches. And any web cache does the same logic. It just checks, do I have a local cache hit for this object, and then I return this object if the TTL is not expired, and otherwise I just forward the request forward in the chain. Okay? If the client requests a revalidation, then the request will get passed through all these caches, and they will all renew their content and serve the new object afterwards. Okay, so when a request reaches the backend, the database loads the actual object, it assigns a TTL, and this TTL will be used by all these caches when the request is passed back to the client. So we have these expiration-based and these invalidation-based caches. The expiration-based caches are managed by this Bloom filter data structure, kept up to date by that, and the invalidation-based caches are directly invalidated by the server-side when a request comes in for an object which is still in some of these invalidation-based caches, the database as a service will decide to actively invalidate this object, for instance, in a CDN. So what this gives us is, as I told you, low latency, of course, because we only, in the default case, have to access a nearby cache. We get reduced database load because the load is distributed over the web caching infrastructure instead of always going to the database backend. We have some protection against flash crowd because when our application suddenly gets very popular, the caches will buffer this load. And some degree of high availability because when the backend goes down, we can still serve cache requests from caches. Okay, so how is the cache sketch actually structured? The cache sketch contains every key of every record X that was written before it expires, which means that might be an object which is outdated in some cache. We do not know in which cache this is outdated because we do not have knowledge of all the caches, but we know there might be some cache which still holds this object. So that's the scheme of determining whether an object has to be in the Bloom filter or not. And if we now do a find request or a read request for an object in the client, the way the Bloom filter works is that it takes the key, it maps it over several hash functions into a bit array of a certain length of m, and when all the bits and that positions are 1, then we know that the object is contained in the Bloom filter, possibly false positive, but no false negative. And then if all these bits are 1, then we do a revalidation telling all the caches refresh your local state, and if not, we do a normal request and get the object very fast from the cache. So that's the general scheme. So what do we solve with this? The first and most important problem that we solve with this is slow initial page loads. So as I told you in the motivation part, slow initial page loads are very business critical. And we can solve those through what we call cache initialization, and that's nothing else but transferring the Bloom filter at the beginning of a session to the client and then let it use it for fetching the data from caches. So the way it works is that when the client comes online and does the initial page request, for instance on the HTML page, it will get this object and also the Bloom filter. And when now a different user or a different application changes some object, we do have to consider stale objects, for instance in our browser cache. We invalidate the invalidation-based caches, add the object with the server-side counting Bloom filter. The counting Bloom filter is just a variant of the Bloom filter, which is able to keep track of deletions, because that's what we have to do when objects are no longer marked stale. We have to remove them from this structure. And then the flat Bloom filter, so the normal Bloom filter, is transferred to the client, and then he can do his hash lookup and tell whether this object he's just requested is stale. If it's stale, he will do a revalidation request, and that will load the object from the server side, the consistent side, and will update all the caches in between. So what this actually does in the end is that it treats every object through this Bloom filter as though it was delivered ahead of time with the right TTL, as if it was known in advance. That's what it actually does. Okay, so when the object is expired because the TTL has passed and we know there can be no other cache which still has a copy of this object, the server will remove this entry from the server-side Bloom filter. And all the caches, all the clients will be able to read it again in a consistent manner. So this is just an example of how big this Bloom filter gets. If we have a certain false positive rate of 5%, and we want to store 20,000 potentially stale objects in this Bloom filter, it has a size of roughly 11 kilobytes, which is roughly the size of the initial TCP window. So the first request to a website can have this size and still fit in one segment at the network level. Okay. Now the second part is at runtime of an application we also want to get fast reads, and what we have to do is we have to guarantee this property called data atomicity. And data atomicity is just this property of guaranteeing no read will ever be older than this delta, it's the amount of time. And what we have to do in order to achieve data atomicity is we have to load the cache sketch, then do our fast cache read operations, and when delta seconds exceeded, we have to do a refresh of the cache sketch. So very simple scheme. And the last part, and this is a bit more involved, so I'll only skim the surface, is that that we can also use the cache sketch to improve optimistic concurrency control. And the way that is done is that simply at the beginning of a transaction, we load the cache sketch, then do all the cache reads during the transaction, and at the end of the transaction, we commit our read and write sets, including the read versions from the caches. And then the server can do a validation, for instance, backward-oriented optimistic concurrency control, and then after this validation can make the writes of the transaction visible. And the part that this cache sketch now plays in this overall scheme is that if we allow reads to be cached during the runtime of a transaction and potentially a retransaction, then we can minimize the overall time it takes for this transaction to finish. And it's a well-known result from transaction processing. Jim Gray proved it back in the days, that the longer an optimistic transaction takes, the higher the abort probability will get. And there's sometimes even an exponential dependency on the transaction runtime according to the abort probability. So the shorter the transaction is, the lower the abort probability of an optimistic transaction is. And we can drive the overall transaction duration down using the Bloom filter and the cache reads without losing any additional consistency. Okay, I'll also just mention the problem, not how we solve it. TTL estimation is important because we do still have to provide TTLs. If the TTLs are very off the actual TTL when an object is written the next time, then we will have a long window where the object is contained in the Bloom filter and will always be revalidated. So no cache hits at that time. And therefore we want to have TTLs that correspond well to the actual time an object is written the next time. And that's what we call TTL estimation. So the trade-off is if our TTLs are too short, we have very many invalidations, but less stale reads and lower cache hit rates. And if we have long TTLs, we get the maximum cache hit rate, but have to perform very many invalidations and have a long window where we can only do read validations. Okay. The way to solve that is by keeping track of all the reads and writes and then do an approximation of the stochastic process, and then you can estimate what the optimal TTL is per object. But let me quickly jump to what this actually brings in terms of performance. So what we did is we evaluated it in two ways, because observing web caching in the wild is kind of difficult because you do not always know which kind of caches actually play into your observation, and therefore we had a dual approach where we built a simulation framework to test all the parts of the infrastructure, and then we did some real-world tests for this scenario. We have a client in Northern California and the database as a service in Ireland in order to have high latency between them, and then we did a simulation. And this simulation uses 90 requests as of 2014, the average number of requests per website, and when we then do an initial page load using these latency distributions, then for a cache hit rate, as reported for instance by Facebook, which have a 66% cache hit ratio in the browser cache and a 20% cache hit rate in the CDN, we would get a 2.5 improvement in initial page load time. The difference between this approach and all the other approaches that already use web caching, of course, is that we can cache every object, dynamic objects, database objects, images, and whatever, because they are all kept up to date using the Bloom filter. We do not have to keep track of which objects are actually, cannot only store read-only objects, we can store all objects. And that's the difference to classic web caching. So how's real-world performance? This is the standard NoSQL benchmark YSSB, the Who Cloud Serving benchmarks in two workloads, a write-heavy and a read-heavy workload. And for the read-heavy workload, we roughly get a 5 times latency improvement, simply due to caching with the same consistency guarantees. Okay, so that's about the caching part. I only have a little time left, I see. So let me get down to the actual new stuff in here. So our overall idea is that we let the application designer define his
requirements in form of SLAs and attach those SLAs to his database schema. Then this database schema is passed to a service provider and gets matched against the available databases, and then the service provider makes for every item inside the schema makes a choice which database best supports this part of the schema. And then during runtime, a mediator sits in between the different databases and the application and routes all the requests according to the model found in this resolution step. So the interesting part is the resolution step. So how do we take the schema and find which database best suits our requirements? And I want to quickly show how the algorithm works. So suppose we have a schema annotator, for instance, with our customers table, we want linearizability, so strong consistency. For a shopping basket, we want high availability in order to always support e-commerce. And we want low read latency in order to achieve fast logins of users. That's what we want from an application designer's perspective. Now, how can we implement that? So what the rank algorithm does, it takes all the available databases. I've taken a few. If there's the algorithm recursively steps through the schema. If there's no annotation, we go to the child nodes, and then if we have a binary requirement like linearizability, we exclude all the databases that do not guarantee it. For instance, Cassandra, Gaussian, S3, and React do not support linearizability due to their quorum-based model, and therefore are excluded. And now at the next steps, we look at the continuous path. So we take the historic values for this matrix, availability and read latency, and calculate the utility function attached to the schema node in order to determine how good they are suited for that requirement. We do that for both availability and read latency and get values, for instance, for Redis and very good, quite good availability and low latency. And we take these scores, pass them up in the algorithm, and pick the database which supports all the binary requirements and has the best overall score for all non-functional continuous requirements. And that's the database we pick. In this case, MongoDB has the highest score, and therefore our routing model consists of route all objects in the customers tables and all queries in the customers tables to MongoDB. And therefore, at runtime, this model is now here in the polyglot persistence mediator, and we can distribute our load and our queries to the database system. That's just the main idea of it. Let me give you an example. So suppose we have we're building a news website, and we deliver a lot of news, and we also have a counter which is very frequently updated. So a mix of high write workload for the counter and high read workload for reading the actual news. And one idea might be to store all this data in MongoDB, but in that case, our counter updates would kill the performance of MongoDB because it would, it would cause high contention at the database level, and then our reads on the news would be badly performed. On the other hand, if we chose to store all this in Redis, which has very high throughput, we would not have to queries in order to retrieve the items that we might want to show. For instance, displaying the most popular news. There's no query language in Redis. So the optimal solution, and that's difficult to come up with, is that we could just split our data model across two database systems, MongoDB and Redis, and store all the counters in Redis and all the documents in MongoDB. It's sorted in Redis in a way that we use a sorted set, so a priority queue, which does support this top K query, which we want to do on our queries, giving the top ranked news. And this mapping would be found by the polyglot persistence mediator, and I just want to show you, if we use this mapping against the primitive variants without polyglot persistence, we get much higher performance. Okay, so I'm only skimming the surface, so if you want to know more about that, you can join me at the poster session. So let me quickly summarize. Okay, I want to mention that because that's what we are currently working on. So I only talked about a CRUD operation and how to cache simple read requests. But it's of course much more exciting to also cache complete query results. And that's what we're working on now. So we have this approach where we take all the create, read, update, delete operations which potentially invalidate query results. We put them through a scalable query matching system, a Storm cluster, matching MongoDB queries. And then on top of that, subscribe to these updates on a query level and now can support continuous queries in the client directly and also update the caches, the validation-based caches, and update the server-side cache sketch. And we can also support polyglot views because this layer is on top of the different database systems. So we could have MongoDB queries evaluated, for instance, over Cassandra or HBase. Okay, that's what we're currently working on. So, quick summary, the cache sketch is our approach to minimize latency. So in order to solve the problem of high page load times in the web, what it does, it uses expiration-based caching with data atomicity and invalidation-based caching with minimal invalidations using the loop filter approach and TTL estimation. And the polyglot persistence side, we want to have declarative SLAs attached to schemas and then let the database as a service provider decide which databases are best for a certain workload and certain service level agreements. Just as a quick outlook, we took all these ideas in order to realize this vision of websites with low perceivable latency and made a startup out of it. This is called Backend. It's a Backend as a service in the cloud. And just to show you that it really works in practice, we compared a simple application with the available backend as a service providers from various different geographic locations, and what the caching gives us is that we are roughly 3 times faster in any case, in any location, as any other backend as a service provider without any tuning from the application side. Okay, yeah, that's it. Thank you very much. If you want to learn more, come see me at the poster session or take a look at our websites. Thank you.
I just want to apologize that we gave a half-day tutorial in 1 hour. but we felt it is important to give you an idea of all the different aspects as a reclaimed backend as a service system needs to cover and how to do that. And now you have a feeling of all about that, and if you have questions, we are there for the week.
Thank you, sir. Do we have questions? It was a microsecond faster. He performs better.
Quick question. Your polyglot persistence approach is based on schema annotation. We've heard this morning that we have schemaless databases in the NoSQL world in a lot of places. So obviously there is something like a schema on top of schema or a meta schema that you can envision how an application uses the schema flexibility. So my question is, when you talk about schema, what do you mean?
Yeah.
Basically, and could you evolve that to support these type of new applications that use flexibility in the schema in a certain way, like using key value pairs within a column family or something like that?
That's a really good point. So our approach to solving this duality between having schemaless stores and having a need for a schema in order to validate the data is that we build this schema which is applicable across databases. So we have a very general schema which has all the different data types which are possible, which allows nesting and inheritance and all this stuff. But as a twist, it allows to have JSON and JSON arrays as a native type. So there's a mixture of having predefined fields which are always of the same form, and then having some unstructured parts which might be changing and therefore are schema-free in that sense. And therefore we have this mixture inside the schema of having a certain part which is schema full and schema-less.
One of the possible usages of this polyglot persistency, which is kind of related to my talk this afternoon, is do you have experience how to mix different consistency models in that, so that you're using maybe a data lake implementation that has very good write throughput, on the other hand assuring on a micro level of data necessary consistency levels? Is there any practical experience? Is it working out?
Yeah, that's definitely work in progress. It's really one of the most difficult parts in building this polyglot persistence mediator is thinking about which consistency guarantees can we actually give. So if we stick together two systems which provide some consistency guarantees, it's not guaranteed that the overall system now guarantees the union of both consistency guarantees, but rather will be the intersection. So it's actually very difficult to align those consistency guarantees. That's true.
Thank you. So next speaker will be Graham Sherland. He is the chief scientist of Flexiant. He has a lot of involvement